Welcome everyone. This is a recording I'm doing for my Mile High video tutorial that I gave. Sadly, it wasn't recorded, so I figured next best thing, why don't I just go over the slides with you and narrate it in this video. That's what you're listening to now. So the presentation is the AV1 video compression standard key tools and why they work. Given as about a 1-hour tutorial, I think it'll be a bit shorter in this video because I'm not taking questions and it's going to be a bit shorter in some of the explanations. I think it's even more important now that this is in video form and everybody can watch this to kind of scope out a bit what this tutorial was for or what it is for. Everybody's got kind of a different AV1 journey right now. I think AV1's very popular. One of the key takeaways from Mile High Video 26 was just so many people now looking at experimenting with AV1 and trying it out. This tutorial was built to explore engineers working with AV1 or trying it out, technical leads trying to make decisions about how they're going to integrate AV1 and what tools they want, decision makers evaluating cost, quality, and trade-off. Obviously, if you're looking at AV1, what you're interested in is the benefits you get for the costs that you're going to spend. Right, so you're going to save probably on bandwidth, on storage. These are the things we're going to look into. What this talk is not, or what this tutorial is not, is this is not going to be this complex codec thing. You don't need to know transform math. You don't need to know deep codec knowledge. You don't have to have prior experience either with codec specs or just with codecs in general. So I hope that makes it clear what we're going for in this tutorial. You might actually know me from LinkedIn. I'm a video compression researcher. I contributed to the AV1 specifications. I worked on Chroma from Luma. I've also have hands-on experience with the production codecs. I've worked on the David decoder. I worked on AV1, and I also worked on libaom when I was integrating the CFL tools. Currently, I'm an independent consultant. My point of view is you can look at AV1 as this kind of huge machine. You've got all these different coding tools, all this different stuff. It's very hard to get your head around it. So this talk is really me sharing my years of experience now with AV1 and to get an idea of how it behaves, what the tools are doing, and how it differs from other formats like H.264. This is going to be very high level type of tutorial. We're not going to go into the weeds and the small details. It's more to get this high-level intuition, and we're going to do that by using analysis of AV1 Bitstreams. So there is the AV1 Analyzer tool that was developed by the Dalit team when AV1 was still being developed. So that tool, you can use it online, and it's hosted on GitHub. It's pretty old now, probably would need people to update it and improve it, so that would be a great project if ever you're interested. But we're going to be using that to also have screenshots from that tool. It's hosted online, so you can try it out with your own sequences, but not all the features are there. It's a useful tool nonetheless. There are also paying tools that you can use to analyze AV1 streams. We're going to look at compression results. I'm going to present here results from a study done in 2019 by Ryan Lay at the AV1 Coding Symposium. And what's interesting about that study and why I use it, it's because it turns on and off coding tool, so we get really specific coding tool gains. Think of it a bit like if you're trying to find the breaker in your house for your dryer or something, and you're just turning them on and off and looking at what lights go out in what part of the house until you find out the breaker you're looking for. That's kind of the experiment that was done there, turning on and off all these AV1 tools and basically getting an idea for what each tool does and what combinations of tools do. So usually you can expect this 20-30% gains over previous generation codecs, depending on what numbers you're looking at. But then these results show us specifically what each tool contributes. So that's interesting. But I really want to focus that this is not about focusing on raw numbers. The idea is not to memorize how many coding modes there are, or what percentage you get from each coding mode. It's really just more to get an understanding. And I think Richard Hamming said it best, the purpose of computing is insight, not numbers. So we want to understand why, not memorize every part of the codec and how it gets gains. So what's the state of AV1 right now? If you want to have a good snapshot of AV1 in production right now, I think the best graph I can show you is this from the study made by Meta. This chart looks very intimidating at first. There's all these data points. It's not clear. So let me kind of simplify this for you. So if we look at the x-axis, those are like cloud compute bags of money, right? The more you go to the right, the more expensive things are. Do notice that this is log scale, so the numbers go up very quickly, so the money goes up pretty quickly. On one side, it's cloud compute cost or money, and then on the y-axis, this is kind of like delivery money, if you want, or bandwidth and storage bags of money. The higher you are, the more expensive things are. If we look at this graph, we can see that AVC is the purple line, so that's H.264. And we can see that while it is more to the left, so cheaper in terms of compute, it's a lot more expensive in terms of delivery. And that's probably one of the first myths that I want to talk about, is the fact that AV1 is slow. In this case, AV1 here, SVT AV1 is the red line. And you can see that in terms of compute, the purple and the red line overlap, right? So for the same compute dollars, you can get delivery savings from AV1. And that's what we're going to look into in this tutorial. You can see that H.265 is there as the light blue curve. There's also libVPX, which is the green curve. EVP9, which is the orange curve. That's an encoder that I worked on a bit when I was with tutorials. And VVEnc, also dark blue. And you can see that for VVEnc, you can spend considerably more compute money to get even more savings in terms of delivery. All right, so let's do like a practical example. We're going to have a running example for this tutorial. So we are going to encode tiers of steel. I call it the I want to be awesome in space scene. So from frames 600 to 720, we'll have basically 260 frame GOPs, so 260 frame groups of pictures. So just for a scale, the uncompressed reference is HD, so 1920 by 1080, 120 frames, 8-bit RGB, so that's about 750 megabytes. So that's a lot of data. Obviously, we want to compress this. We don't want to send it out as is. To do so, we're going to use ffmpeg. The command looks something like this. You'll say ffmpeg, give me as input the file. In this case, it's in Y4M format. I want to encode 120 frames. Pixel format is YUV420, which this is chroma subsampling. The difference between encoding with H.264 is instead of saying libSVT AV1, we would say lib H.264. So in this case, we want to use AV1, so we say libSVT AV1. Preset 0. So preset 0 is probably not something you would use in production. In this case, I just want to use it so that we see all the coding tools. The presets are the dots that were shown in the previous graph, so the M1, M2, M3 that were on the red curve. So in this case, preset 0 is the slowest, but has all the tools. And then obviously you want to pick and choose a preset that makes sense for your operating point. So CRF is basically the constant rate factor. We're going to use 32, which is mid-quality operating point. You might use something different. You could use rate control, so you could actually specify a target to reach, so maybe 1 megabit per second or whatever, something like that. We're going to specify that our group of pictures is 60, and we are also going to turn off the scene cut threshold. So basically, we just don't want the encoder to try to do scene cuts. What we're going to find out is that iframes are actually quite expensive. Proof of this is we can see it here. This is the file that we've encoded. We can see that we went from 750 megabytes to 0.74 megabytes. So that's pretty good compression. PSNR, which is quality if you want, is 40 dBs, which is pretty good quality. SSIM, another measure of quality, gives you 0.96. Again, that's pretty good since it goes all the way to 1. So it gives us an idea that we've got pretty high quality encode here. What we're seeing is that the iframes take up about 30% of the bits. The first frame is an iframe, and then we can see that around frame 60, so here we have another iframe, and that's the beginning of the second group of pictures. And just these two frames take up 30% of all the bits in the encode. As for p-frames are the second frames that are here. It's important to understand that this ordering is coding order, and it's actually not display order, which means that in this case we'll have frames that are coded out of order, and this way it allows us to get these references to things either in the future or in the past. So P frames are frames that are predicted directly from the iframes, and these again make up 21%. So you have the second frame here, and then this frame here. Just with your I and P frames, you're already at half of the bits of the sequence, right? So 1/2 of the bits goes to these 4 frames, and then the other half goes to all the other frames. In this case, we have 120 frames, so 116 frames share the other half, and 4 frames share 1/2. And that's just the state of things right now. And again, you can see that if we were to break down that 49, the percentage is going to be distributed on a few frames, and that most of the frames get very little bits. And we'll figure out why a bit later. All right, so what does AV1 do? So now we've got these I frames and these P frames. How does it break them down? So inside of a frame, you're going to split that frame into blocks. And one of the things that are interesting in AV1 is that you can actually have a lot of block sizes and a lot of very big block sizes. So just to give you an idea here, comparing it next to H.264. So H.264, you would go from 16 by 16 and going all the way down to 4 by 4. You could do this by either doing a vertical or horizontal split, or just do a normal split, which breaks it down into 8 by 8s, and then from there you could do again vertical or horizontal, and then split again all the way down to 4 by 4. Whereas AV1, you can start at 128 by 128. You've got your vertical and horizontal splits. You also now have T-splits. From there, you can recurse down to 64 by 64 blocks, and notice that we also have these 4-to-1 and 1-to-4 blocks here that show up, and this gives you just another strategy to break down blocks even more. So you can signal again in a split, and then this split would bring you down to 32. Signal another split, go down to 16, and signal another split down to 8. And finally, that last split would bring you down to 4 by 4. So we're trying to do 2 things here. One thing we're trying to do is, with these different shapes of blocks, we're trying to actually model the edges or the content of the block as closely as we can, and we're going to see this very soon. On the flip side, what we're also doing with these bigger blocks that have simpler shapes is have these big blocks for parts of the image like the background or smooth parts of the image where nothing really happens. We're trying to do 2 opposite things: model the smooth regions very well, and at the same time model structure and edges very well. We can see this in action here. This is the iframe from our sequence, and you can see that the blocks that are here, the big blocks, those are all the 128s by 128s. We can see that for the background, it just uses the biggest block and doesn't split it. One of the reasons why this is interesting is that if you have bigger blocks, not only do you have less signaling, but you also have bigger transforms, and these bigger transforms allow to compact the energy more. That way you can have maybe just a few coefficients, maybe, I don't know, 2 or 3, 4 coefficients, sometimes just 1, and that's able to model the entire block. So for the 128 by 128, you have 1, 2, 6, or 8 different coefficients, and that's it. The edges are now being taken into consideration, and the block decomposition tries to match the structure. And again, the idea here is that by matching this with these more precise shapes, we don't end up going into these very small blocks. So here, if you look at an H.264 rendition of this, you would get just all these small 4x4 blocks at the edges, because that's the only tool that has to model edges. Whereas here, there's more tools. So we have these 1-to-4, 4-to-1s here. We have a T-split here, so we can see all these different tools in action, and this allows us to model the shape properly. What we're trying to avoid is having an edge in the middle of the block, because then we'd have a problem, because we would need different information to code one side of the edge versus the other. If we can simplify edges into blocks that are very similar to one another, that don't have discontinuities in them, then it's a lot easier to code them. That's what we're seeing here. At the same time, we're trying to break down as little as possible, because every time we break down, we need to signal more, and we're going to need to have more coefficients to code what's going on, and that's what we're trying to minimize. You can see the encoder doing a pretty good job here, breaking that down. So what are the gains? How did this help AV1 get better? This is results from the study I talked about earlier, which started with a 8x8 to 64x64 square-only partition scheme. So that was the baseline that was used. If we start at the bottom, they looked at adding rectangular blocks in the structure, and already if you add rectangular blocks, you improve coding efficiency for the same level of quality to about 3.77%. In the codec space, that's good. Like I said before, if we're looking at this idea where from one generation to another, there's about a 20 to 30% improvement, getting 3% just for rectangular blocks is pretty good. If we add rectangulars plus T-splits, we get 4.15%. Rectangulars and 4 to 1, 1 to 4, we get 4.65%. If we have everything together and add in 4x4s, then we reach 7.86%. What's important there is the 4x4s add considerable gains here. Having more flexibility when you break down the structure is better, but 4x4 also gives considerable gains. If you add in 128 by 128, you get slightly more, but not that much more. The reason for that is that in AV1, you actually don't have 128 by 128 transforms. There's not much gain in terms of energy compaction when you're going from 64 by 64 blocks to 128 by 128 blocks. All you're saving is just the signaling, which is not that expensive at that level because 64 by 64 blocks are already pretty big. You're not saving that much. You're saving the signaling for, instead of 4 blocks, 1 block. But then you pay a penalty where your prediction is less precise. The trade-off there seems that while there is a small gain from going 64 by 64 to 128, 128, because of the reasons I just explained, the gains are rather small. But 8%, again, if we keep that in perspective, that's good gains for Intra AV1 there. Now what we're going to talk about is AV1 Intra Prediction. The block partitioning I described earlier worked over all the frames. Whether you're doing intra frames or interframes, you divide your blocks like we just saw. Now, there's going to be 2 types of frames like we talked about before. The intra frames, which are frames that are only predicted from content of the current frame, and then you'll have interframes, which are predicted from previous frames, so where you would use something like motion vectors. Focusing on intra frames, what's new in AV1? The big contribution to intra frames or intra prediction is mostly directional modes. You have an edge in an image and you want to model it, and what AV1 has is a lot more angles at which you can draw your edge inside of a block. But that's not all it has. It also has improved modeling for flat and smooth regions. These are regions in the image that don't have edges, but they will have different properties, and we'll see 3 tools that have been added to better model that. There are also other tools that were added. One is recursive prediction modes. These are prediction modes that are predicted from the pixels inside the block that's actually being predicted right now. So that's the recursive thing. Imagine you'd have a 16 by 16 block, you want to encode it. You could split it into these smaller blocks, encode, and then from those predictions, predict the other parts of the block. Another tool that's in AV1 is filtering of reference pixels. When you're going to build an intra prediction, you're going to use neighboring pixels from blocks that have already been reconstructed. What you can do is, instead of using these values directly, you can apply a filter to them. Imagine you're smoothing them out. And the reason for that is to make them into better predictors. So these directional modes now, let's have a look. H.264 had 8 base directions. You can actually see them here as the dark gray lines. These are directions you could use. Based on the reconstructed pixels of the neighboring blocks, I want to make a prediction, and this prediction will follow an angle. The simplest examples is the horizontal and vertical. So if you're going horizontal here, what you're doing is you're going to take the neighboring pixels and you're just going to copy them in and just copy them this way. So this pixel gets copied here, 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 so horizontally. So the entire line is just that value repeated. On the flip side, if you're doing a vertical prediction, then it's going to be the top neighboring pixels and they're just going to be copied downwards, and that's your prediction. Now, if you're going to have an angle, it's a bit more complicated, but you get the idea. You're going to follow the direction of the content. What's new in AV1 is that we're going to add 6 delta angles. It gives us these increments of 3 degrees. You have 3 values of 3 degrees before and 3 values of 3 degrees after. And you can see them here. That effectively gives us now 56 directions instead of 8. So you pick your base prediction, you set your delta, and then you get an angle that looks like this. For the smooth part of the image, or parts of the image that are flatter or changeless, there's 3 coding tools. The first one is DC Prediction. DC Prediction was also in H.264. The idea is you take your reconstructed neighboring pixels and you just average them and put the average everywhere. You just paint that in and it gives you this nice flat block. That's super useful when you have a smooth region. Path Prediction, this one is kind of flat but also edge aware. You're going to look at the top left pixel. Let's say in this case we want to predict this P pixel here. We're going to look at the top left pixel, the top pixel, and the left pixel. We're going to use this equation here. Don't worry, this is the only equation I have in these slides, so don't be scared. So we're going to take the top pixel, add the left pixel, and then subtract the top left pixel. We're going to compare each of these pixels to the result from this equation, and we're going to take the closest one. Imagine that you would have an edge or something that would change the content, but maybe top left and top are going to be similar values, and then this value is going to be different. What you want to do is you want to be able to pick up on that and pick the closest value. So once you're on the other side of the edge, you don't want to match that content. At the beginning, maybe on top here, you're closer to top. So you're going to use that value, and as you go down, you might start using the left value. The final one is a smooth prediction. What you're going to do here is you're going to use 2 different linear interpolations. You're going to interpolate the top part to the top right and the left part to the bottom left. You average both linear interpolations, and that gives you your prediction for that pixel, and you'll do that for all the pixels in the block. What does AV1 Intra Prediction look like in practice? We can see that all the dark reds are DC predictions. When I was saying DC prediction is quite good, we can actually see it that it gets used for half of the blocks in the sequence. After that, the second most popular mode is vertical. So the purple blocks, you can see them here, and then horizontal, you can see them here. Smooth also is the yellow blocks here, so that's about 6%. If we look at all the other directions, so here we have a zoomed in version again of the woman being intra-predicted. You can see that the directions in the analyzer are actually shown by arrows inside the block, so you can see the different directions. Now all these different directions combined, except for vertical and horizontal, give you about 12% of the blocks in the image. So it gives you a good idea how the image is built up. Again, we see that the edges kind of follow the content, and that's exactly what we're trying to do here. We're trying to model this content, these structures, with these blocks. The better the prediction is at modeling this, then you have a smaller residual, which is the expensive part to code, and you can also use bigger blocks. So again, less signaling, more energy compaction. These are the ways in which AV1 can gain when compared to previous generation video codecs. All right, intra predictions, where do we get the gains? So the big part of the gains is really going from 8 angles to 56 angles. We can start there. You get 5% just by doing that. By increasing the number of angles, you're close to most of the gains you'll see in Intra. If we go tool by tool, so path prediction, 0.33, The reasons for that is that this mode is specific to a type of content. It doesn't incur that much. Filtered reference pixels, we talked about that before, this idea that you can actually filter the prediction pixels you're going to use to improve prediction. That gives you 0.82%. Just to give you context, gains like that seem small, but in video coding they're actually considerable, so these tools were added and accepted. Some people might say, why do you do this for such a small gain? But the answer is all the small gains will help. Smooth prediction, 2.36. Of the Intra Prediction modes for flat content, smooth was really one that gave the most gains. You add everything up, you don't get 8.70% because all these modes are competing with one another. So you can only pick one. When you're doing these on-off tests, you can always have smooth prediction doesn't compete with the directions and things like that. Whereas now, when we combine all the tools, then only the best one wins. The exception here is filtered ref pixels. So filtered ref pixels can be combined with other of the solutions, but for all the modes, they compete with one another, but still we see 8.7% gains. That's very good, again, just for the Intra tools. After that, so we've talked about Intra Prediction, now we'll talk about Inter Prediction. Before AV1, if you looked at the formats like H.264, the main way you would do interprediction is through motion vectors. You're assuming this kind of rigid body translational model. In other words, objects that just kind of translate, that just move. And that's kind of limited, right? Because objects can translate, but they can also rotate, they can resize. Imagine you're zooming in with your camera on something. They can also be illuminated differently. There's all these things that the translational model doesn't model well or doesn't explain well. And that's where the gains are, right? Because you're not going to do better translation. We already have translation. Where you're going to get gains is in new tools. So you can have things like compound prediction, which will help you handle occlusions, objects that are going behind one another or being hidden and then coming back out. You'll have wedges in AV1 that look at object boundary and the structures. You'll have overlapping block motion compensation that will remove these discontinuities at block edges. And you also have a warp motion mode to model these non-translational motions. What you need to understand is in AV1, it's not really to pick a motion vector, but it's really more to model motion uncertainty, right? So it's a lot more about motion modeling than it is about picking motion vectors. All right, so wedges. You want to be able to blend two different predictors from either past or reference frames. You can have one of the predictors be intra, and what you're going to do is you're going to apply a mask to decide how you're going to split the block. We can see the different masks here. So all the black pixels belong to one reference, all the white pixels belong to another reference, and you can pick this mask that fits the content. The idea here, so when we were talking about block decomposition before, a very important part of block decomposition is being able to model the edges. Well, this again allows you to do that. I've made an example here, kind of drew this out on top of the analyzer, but you can see that the hair part here with the background, what we're going to try to do is take a mask that would be able to model this. Because the woman is turning her head, you won't find exactly this image in either a previous frame or a future frame, but you're able to get, make this structure out, get a part of the hair from maybe the future, then get the part of the background from maybe the past, and then you're able to blend that together. What's interesting is you don't need to break that down into smaller blocks, so less signaling, and you can use like a bigger transform here, so you have bigger energy compaction. So OBMC is a bit different. OBMC is the idea that for smooth regions of the image, right? So think about that background with the trees, you'll have a lot of blocks there. Now the problem with that is that these blocks are locally optimized. And what that means is when you reach the edge between two blocks, you might actually see a discontinuity because of the motion vector is not pointing to the same value. The idea behind overlapping block motion compensation is that you're going to take your motion vectors from the block above that's already been coded, and you're going to take the motion vectors from the block on the left that's also already been coded, and you're going to extend it into the region that you're trying to predict, while also making your own motion estimation for that block. So we're seeing this example here. This is a fabricated extreme example where you would have motion vectors going this way for the top one, and motion vectors going kind of here to the left for the left one, and then very bizarrely you'd have this motion vector going down right here for this part. If you code that, you're going to see discontinuities here because that content won't match up. So what we're going to do, we extend our prediction in these different directions, and we're going to blend all three of these together. This will give us a nice smooth transition between the blocks. The logic here is that even though there's these discontinuities between the local optimization, the idea is that these edges would not be in the background because this is a smooth background. If there actually was an edge here, then you'd have these block decompositions that would be a lot more aggressive and trying to model it. If we see edges in the reconstructions that aren't in the original source content, then most likely it comes from these discontinuities caused by the fact that we use different parameters, different values, different motion vectors in this case, between adjacent blocks. By blending it, we remove a part of that. Another thing that's in AV1 is warped motion. So the idea of modeling non-translational motion. The idea here again is that in real world, not everything is rigid body translational motion. AV1 gives you different tools that allows you to express different types of transformations. You can do rotation, you can do scaling, and perspective here is wrong. That's a typo. It's a skew, right? So this should be a skew. This way, we actually get more from motion compensation because we're able to warp the motion to make it better fit what's actually going on in the image. So you have examples here of scaling, right? So imagine your block gets bigger, so you can just stretch the pixels inside the block. It doesn't change the size of the actual block, it just stretches the prediction inside. Same thing with skew. You could actually skew it on one side or another, and you could also rotate the block. So now it's important when you look at the analyzer, the block is not going to rotate inside the analyzer. The block stays the same. It's just that we apply a transform to the pixels inside of a block to make the content rotate inside of there. What are the compression gains? Again, based on the study we saw where we turn tools on and off. So global motion here gives you about 0.40%. Global motion is warp motion, but applied globally to the entire frame. Warp motion is applied locally to specific blocks. Global plus warp is just combining both of these together. So we see about 2% there, which is good. Overlapping block motion compensation is 3%. And then if we combine everything together, we get 4.41%. While these modes here can compete with one another, wedges actually don't compete here. So you could actually combine wedges with that, and wedges give 7.23%. So that's actually very good. That gives you an idea of where you would get the gains in AV1 for Intra Prediction. Now that we have these improved Intra Predictors, the predictions themselves are very good. And that creates a situation where you can actually just not encode a residual. So the residual is basically the prediction error, right? And that's what costs a lot when you're doing video coding. You're going to have a prediction, then have as a residual, and that's what you code. But what we're seeing now is that the prediction can actually give you a very good frame, and you can actually skip residual coding on some of the blocks. And this is an example we're seeing here from the sequence we encoded. All of the purple blocks are skipped blocks. In other words, we just use the prediction itself, good enough, and we don't need to do residual quantization, entropy coding, all that stuff. We do send all the signaling for the block decomposition, but not the actual coefficients. That's pretty good, because as you can see here, most of the frame is skipped. This block I find weird because I figure, feels like this one should be skipped also, nothing really going on there, but the encoder thought it would be better to code it. So we can see these edge blocks where maybe there's rotation or these transformations that are harder to model. These need to be coded with coefficients. This part here also, maybe water's moving, not sure, but we're coding that. For everything else, you can skip. So that's why, if you remember back when we looked at the number of bytes per frame, you might wonder, how do you have these super small frames that have almost no bytes? Well, that's the reason why. It's because most of it is skipped, so we just signal the block decomposition. And again, because the block decomposition uses entropy coding, it makes for recurring blocks to be very cheap. All right, so now that we've looked into the coding tools, there's also what are called in-loop filters in AV1. Now, I want you to think of these more like cleaning tools than coding tools. What you're going to do is you create your prediction, you encode your residual, you reconstruct the image, and now you're going to look at the difference between the reconstructed image and the reference image. What you want to do is kind of clean that up. So you want to remove error as much as possible. There's 3 different filters that target different types of artifacts. Probably the one that's most well known, because it was used also in previous standards, is deblocking. We have an example here of blocks or blocking artifacts. And these are what we talked about with OBMC before. So this idea that since blocks are locally optimized, then when you reach a block boundary, there's a discontinuity because you're going from one optimization to another, and it's just a very sharp transition. So the deblocking filter, what it does is try to smooth that out. So we're going to try to smooth these edges, and again, under the assumption that if there wasn't an edge in the original image, then this is an unwanted edge. It's an artifact that was created and we want to remove it. So we just blend it out. CDEF looks at ringing. So ringing, as you can see, is if you have an edge in the image, it might be that because of the quantization that happens to the transform coefficients, there's a bit of bleeding or ringing that happens where some of the data is represented outside the edge. We can see this here. CDEF, what it does, it actually detects the edge here and then filter along the edge and then perpendicular to the edge to clean this up. And then obviously the encoder can specify different strength here so that it's able to adjust. Again, it wants to make sure that it preserves the edge in the image. The idea is not to wash out the edge, but to wash out like the artifacts that we see or the bleeding that we see along the edge. The final in-loop filter is a loop restoration. What it does is that it looks at reconstruction error. So it looks at the error once you finish reconstructing your block compared to the original frame. And what it's going to do is filter that out as much as possible. It's going to try to find these optimal filter coefficients to clean up the image and remove as many artifacts as possible, while deblocking only occurs at block edges and CDEF occurs at real edges in the image. Loop restoration can be applied mostly everywhere. That creates a situation where the filters also kind of compete. So that's why the results aren't additive. So you can't add them together and get exactly the same value. We would be expecting to get about 10% gains from adding CDEF and loop restoration, and we're more closer to 8%. Still, 8% is very big. We don't include deblocking here because deblock was already used in previous video formats. If you're looking at the gains for AV1 in terms of in-loop filters, CDEF and loop restorations are where the big gains are. So now that we've seen all this, we've got an idea of the different things we'll find in Intra Prediction, different things we'll find in Inter Predictions, and then the different in-loop filters. You might have been wondering, okay, how is it that we can get all these red dots? Remember the line I showed at the beginning of the presentation where you saw SVT AV1 with all these different speed settings? You might have wondered, well, how is it that we do it? Why is it that encoders can have these different use cases and have these different trade-offs between speed and quality? Well, the reason for that is that the presets will just turn on and off tools. You can see an example here of the different tools we looked at today and what speed presets are enabled or disabled. We started today with block partitions. So let's look at that. We see that the maximum size is 128, and that happens all the way until we reach preset 7. And preset 7 will actually drop down to 64 by 64. We talked about why that is, right? We said, well, there's not that many gains because AV1 doesn't have these bigger transforms, so there's a small gain there, but at some point, it's just not worth it to evaluate these 128 by 128 anymore. At speed 7, we just stop at 64 and pretend they don't exist. So we'll never be able to signal them, but the flip side is we don't need to search them, so it's faster. Same thing here with the min size. So from 0 to 2, we'll go all the way down to 4x4 blocks, and we saw that before. That gives you some good gains in terms of rate distortion. These smaller blocks are actually very beneficial, but they're slow to search. So when we go to preset 3, for example, we'll just stop at 8x8, and we will not do the 4x4s, and we keep doing that all the way to the end. The idea is that we will never signal a 4x4, probably, because we're not searching for them, and we get a speed up from that, but we also lose out in terms of compression efficiency that we can get. Intra Prediction, all the modes are turned on, so we don't really need to worry about that. Warp is always on, and then global motion gets turned off around preset 5 all the way to the end. Global motion not giving that much gains, and you have to search for it, so at one point it's just not worth it anymore to keep searching. You're just better off saving your compute budget for other things. OBMC, I've just noticed here that there's a little error here. This should be red. We see on all the way to 9, and then turned off at 10. Wedges, so they're turned on very early, and then because of all the different wedges you need to search, that makes everything a lot more complicated, so they get turned off very quickly. So we do lose these gains here, which were about 7%. As for the in-loop filters, deblocking is always on. Deblocking can give good gains and is relatively cheap to compute, so that's why it stays on. CDEF is always on, and then loop restoration on until M10, and then it gets turned off. You need to understand that what you're seeing in the documentation is the tool is turned on and off. The directional here is going to be a good example. We said there's 56 directions. It might be that they're on all the time, but here you'll have 56, and then here you might have, I don't know, 42, and then here you might drop to 30 or 28, whatever, and you'll keep dropping down like that. So the tool is still on, but it's limited. CDEF is another example here where you would do something like that. So you will constrain the search space while keeping the tool on, and that allows you to go faster. I want you to think about this as when you use the speed presets, it doesn't change AV1, right? AV1 remains the same, it's the same format, but it does change what or how hard the encoder is looking or searching for ways to encode the frame. All right, so going back to this graph we had from the beginning, we can actually see these different presets now that I was explaining. So M0 all the way to M10. Past M10 is something less used. My understanding is you're better off going from M0 to M10. There's just a lot more things being disabled at that point. You can see the different speed settings of H.264 and how they overlap. And now you understand what that means, right? It's the trade-off that you're doing, how much money you're trading off for compression efficiency. What I want to highlight here, that's what we started this presentation with, is the fact that you actually have in AV1 an H.264-like operating region, right? So in this range here that I've highlighted, you can spend the same amount of dollars for H.264 encode as you would for AV1 encode. But then you get considerable saving. It's not, should I take H.264 or should I take AV1? It's not like these things don't overlap. There's a big overlap, and you can see where it is and the trade-off you're doing. You might ask, well, why is it that there's just such a big gain to be had from H.264 to AV1? And the reason for that is, what we talked about, the fact that there's better predictors, either intra or inter. It's got bigger blocks, it's got loop filters. So even if it has the same compute budget as H.264, the AV1 encoder has more tools, and it can look at a subset of tools that give gains compared to H.264 for about the same quality. If you wanted to, you could push it even further and say, well, I'm going to restrict AV1 to run in an H.264-like set of tools. So I would limit the sizes to 16 by 16. I would limit the intra predictions maybe just to the 8 based. prediction, I would turn off things that aren't in H.264. It wouldn't be an H.264 compatible bitstream, obviously, but you would have reproduced as close as you could the H.264 tools in AV1. What we're seeing is that given the complexity budget of the H.264 tools, since there's more tools in AV1, some are better, some go over bigger regions of the image, we can actually get away with, for the same compute budget, better predictors, bigger block size, and more efficient loop filters. That's why you get better storage or improved compression for the same level of quality and the same amount of CPU budget. All right, so that was quite a big talk. We went over just a few small things, but if you look at these tools, I think that's a lot of where the contribution come from in the AV1 coding game, so that's why I focused on these tools. You can see that we talked about Intra Prediction, Inter Prediction, and loop filtering. This is what we covered. There's obviously a lot more to cover. We didn't talk about transforms. We didn't talk about quantization. We didn't talk about entropy coding. We didn't talk about film grain synthesis. So there's still a lot left on the table. Probably opportunities there for me to give more tutorials. The idea was to get you started on your AV1 journey, that you get an understanding a bit of how speed presets work. A lot of the parts where the speed presets change are these parts here. There's still some other things that can happen in other parts of the codec, but this is where the bulk of the action is happening. So thank you very much. If you have any comments related to this talk, you can leave them in the comments of this video, or you can look me up on LinkedIn and reach out. Thank you very much. Have a good one. Bye-bye.